Hello and welcome back. In this video, we'll briefly discuss what's called the second fundamental theorem of calculus, and it's the bridge between differentiation and integration. It states that the derivative of the integral from any constant a to the variable x of the integral of f of t dt is simply f of x, which basically establishes an inverse property, saying that the derivative of the integral cancels out. So for this problem here, this example, we're going to find the derivative of f of x, capital F of x, given as an integral. So this is a very short problem, and it takes longer to write it than to actually do it. Our capital F prime of x then is going to just be the integrand, or inside of our integral, evaluated at x. And that's it. There is nothing more for us to do. So let's do another example. Let's do this one in a different color. Do this one in red. We're going to let capital F of x this time be defined as the integral from 3 to x squared of the tangent of t with respect to t. And of course, you could go through and actually find this integral using some substitution and whatnot, but that's not the goal of this problem. The goal of this problem is to actually apply this fundamental theorem. So its derivative is going to be capital F prime of x, and that's going to be this tangent function inside our integral, but instead of being evaluated at t, we're going to use the chain rule. And it's going to be the derivative evaluated at the inside. Well, inside of it is an x squared. And then that's going to be multiplied by the derivative of what's inside, which is 2x. So our derivative is just 2x times the tangent of x squared, and that is it. You will notice that we don't do anything whatsoever with the constant 3 in the integral because its derivative is 0, and it never shows up as part of our definition up here either. It just disappears upon differentiation because it's a constant. So let's do one more example. Let's go through and do the integral, or we're going to let f of x, I should say, be defined as the integral from x squared to x cubed of the rather complicated function 1 over t to the 4th plus 1 with respect to t. So in this problem here, what we want to do is notice that we need to use the chain rule for this. We can rewrite our f of x as the sum from x squared to some constant c of 1 over t to the 4th plus 1 dt plus that same constant c to x cubed of 1 over t to the 4th plus 1 dt. And then we can go through and rewrite the second integral. So actually it'd be the first one. So f of x is going to be the negative integral from c to x squared of 1 over the t to the 4th plus 1 dt plus integral from c to x cubed of 1 over t to the 4th plus 1 with respect to t. And now we are ready to find our derivative using the chain rule. So f prime of x, again, is going to be the opposite, or the negative of, and it's going to be the inside integrand function evaluated at that upper boundary times the derivative of the upper boundary, which is 2x, and of course minus 0, and then we're going to have plus, we're going to have the, once again, integrand function inside evaluated at x cubed, so x cubed to the 4th plus 1 times the derivative of x cubed, which is 3x squared. So simplifying this down, we've got a negative 2x divided by x to the 8th plus 1 plus a 3x squared divided by x to the 12th plus 1. And that is a perfectly acceptable way to leave the answer for this derivative problem. You'll notice again that we did not actually involve that constant c in this process. So again, the second fundamental theorem of calculus is very different from the first one. Again, the first theorem basically talks about the definite integral and area. This is all about the relationship between differentiation and integration. And again, a very powerful shortcut, and if you take higher math classes, you'll definitely be applying this down the road. So very useful to keep this in the back of your mind.